Woohoo, we're back. And I brought my little friend, the Martian, with me because I was missing puppets. So here's our Martian. And we're finally here for part 3 of this problem where we're throwing rocks around on Mars, which seems like a good time to me. And here's the original problem. And we've got the original height function. And remember that we're throwing this rock up at 10 meters per second from the ground. So it's kind of a weird model, but that's where we're going with. And then remember that on Mars is much smaller than Earth, so we get a much smaller acceleration due to gravity. And remember that 10 means positive 10, which means the rock is heading up. And negative 1.86 means that gravity is sucking it down. So we've got orientation in our numbers. And so for this last part, I want to know, when will the rock hit the surface? Now, I'm going to remind you that, and in fact, I said something about it right here. I'm going to remind you that in math, we do not have air resistance for right now, and we do not have terminal velocity. And so that's going to make our model not quite match up with what happens in the quote-unquote real world. But I mean, we've got a little puppet here, and so that'll make everything better. We're going with the simplified model. So we're assuming there's no air to run into the rock or slow the rock down, and there's no other stuff going on. So this is a very simple model where all we have is the height function. So our height function was that we threw the rock up at 10 meters per second. So that gives us the 10t. And then gravity on Mars, pardon me, my friend, is going to pull it back down at 1.86 meters per second squared. And this is times t squared because it's part of the acceleration rather than just the velocity. And here's our height function. And the question is, when does the rock hit the surface? And what you got to think about is, what do we know about the rock hitting the surface? And I don't know anything beyond the fact that if I'm on the surface, that means that the height of whatever t is has to equal 0. It means it's on the ground, right? So, pardon me again, my friend. There are 2 moments when this rock is going to be on the ground, and that's when we start and when we finish. So I'm expecting 2 answers. So let's give this a try. I got 10t minus 1.86 t squared equals 0. And if you review your quadratics, you're going to realize, wait a minute, I don't have to use the quadratic formula. You could, but in this case, I don't have to because I can just factor. I can factor t out and realize that this is going to give me 2 possible answers. One possible answer is that t equals 0, because if you have 2 things multiplied together to give you 0, one of them has to be 0. That's called the 0 property. It's one of my favorites. So you can't create 0. So either t is 0, well, that's this spot right here. At time 0, we're starting on the ground, or 10 minus 1.86t equals 0. Okay, so that means we're actually going to have to solve something. So I'm going to move my Martian friend out of the way so he doesn't get injured. We want to protect the innocent when it comes to math. And I'm going to go ahead and solve 10 minus 1.86t equals 0. I'm going to add 1.86t to both sides. And I'm going to get 10 equals 1.86t, or t equals 10 divided by 1.86. Now, life gets exciting because as mathematicians, we're going to want to find an exact answer. And although this is an exact answer, it's a mix of decimals and fractions. And so that's going to make it somewhat problematic. So if I multiply top and bottom by 100, I get 1,000 all over 186. And then I realize top and bottom are reducible by 2. That's 500 over 93. Now, I happen to know something about 93. 93 does not play well with others. 93 is 3 times 31. So this is not going to reduce any further. So this is our exact answer. We got to remember this represents t, so this is 500 over 93 seconds. And mathematicians everywhere are just like, yay, it's an exact answer. But then, like, the humans show up and they're like, what does that really mean? Is that like 5 seconds, 6 seconds? What is that? So I'm going to bring in my calculator, and 500 divided by 93 gives us this 5.3763 some other stuff seconds. And then the problem doesn't tell me how to round. So generally, if a problem doesn't tell you how to round, you should leave it in its exact, either as a fraction or write out the ... so someone knows that it just keeps going. But I'm going to go ahead and round just for funsies. Let me round to 2 decimal places. So if I round to 2 decimal places, that means I got to look at the 6, right? There's the 3rd decimal place right there. 1, 2, 3. 6 is above 5, so I'm going to round up. So it's going to be about 5.38 seconds. And so that will be my estimate. And this is an approximation, so I use the wiggly equals. This is exact because I'm just writing down what the calculator tells me. A quick note, since we're talking about it anyway. When you get to the very last digit that your calculator shows you, you cannot trust this digit. This digit may be the actual digit, or the calculator may have rounded up. The calculator knows it can only show you this many digits, so it will frequently round this to make it a nicer number. The calculator actually knows far more of the digits. It just doesn't have the space to tell you. On the other hand, to be honest, when you get down, these are tenths, hundredths, thousandths, 10,000, 100,000, millions, 10 millions, 100 million, like 1,000 millionths of a second is getting to splitting hairs, so that in the real world, you probably don't need that much precision. So there you go. Mathematicians versus engineers. What can you do? So the next question, the last question, ignoring air resistance and issues with terminal velocity. So basically terminal velocity in a nutshell, or out of a nutshell, that's falling off a building, basically means that you can only get going so fast. Unless you're in a vacuum, there's stuff in your way. The air will actually slow you down. And so that objects will have a upper limit to how fast they can get going when reapproaching whatever the ground is in whatever system you have. So air resistance and terminal velocity aside, because our model does not include those, what velocity will the rock hit the circuit? With what velocity will the rock hit the surface? Here's the thing. We're expecting that if we're starting here, here's T, here's H, this is T equals 0. We're expecting, and I know I draw such a beautifully symmetric parabola. I know you're all very, very impressed, I can tell. But if this is symmetric, and if the velocity right at this moment is 10 meters per second, what are we expecting will happen on the other side? We're expecting that the velocity should equal 10 meters per second. It's a symmetric system. Now, again, in the real world, when you fire it and when it comes back down, there are reasons why it might not actually be going 10 meters per second, specifically all the air between you and where the rock is headed. So it's not necessarily guaranteed it'll be 10 meters per second in the real world, but we don't have the real world. We have our lovely formula. So our formula says that at time t, the height is 10t minus 1.86 t squared. However, if you recall, in the last video, let me see if I can find that page. In the last video, we found that instantaneous velocity was 10 minus 3.72a. Ooh. At time A, right? Sorry, I didn't mean to push my friend off. There's our friend who's still here, who's still holding on, even though it's calculus, and calculus can be intimidating. And so with what velocity, I cannot say this. I know I wrote it in correct grammar, but I'm questioning this. But for the benefit of our Martian friend, I want to try to get the English right. With what velocity will the rock hit the surface? We know that the time is going to be 500 over 93, or originally it was 10 over 1.86 seconds, right? So the velocity equals 10 minus 3.72 times 10 over 1.86. Okay. You ready for the magic trick? I'm very proud. I'm very excited. Our friend, the Martian, is very excited. Okay, so this is 10 minus. Now, 3.72 is 2 times 1.86. So let's cancel this. Cancels there. So we get minus 2 times 10. So everyone's like, oh no, this isn't going to work out. And I'm going to say 10 minus 20 equals negative 10 meters per second. What does that mean? So up here, when I said the velocity was 10 meters per second, I left something out. What did I leave out? I left out orientation. Since it's coming down, it's going to be coming down at negative 10. Since this is going up, it's going up at positive 10. Our formula works. It works. Yay! Woohoo! I know you're all very impressed. I am so glad that you're so very impressed. I'm very impressed. I feel good. I'm going to go get a little drink because my voice is getting a little strained. And you guys should take time, do something fun, take a break, shake out the old Etch-a-Sketch, and then come on back, because we're going to have more videos. I know, very exciting. Yay, calculus. Woohoo! Math on, guys. Math on.